And do you see my screen here?
Yes, I do see your screen.
And it's full screen? Great. Thank you, Art, and hello, everybody. So I'm Katerina Kekries at the University of Colorado Anschutz Medical Campus, and I'm one of the leaders of one of the UO1 DTC groups, along with the Bashis Ghosh. He wasn't able to make it today. His daughter is graduating, so he was at various graduation events. But on our behalf, I'll be presenting today on our work in the last 4 years. And first, I wanted to thank our team. Looking back, almost more than half of the time was in this weird COVID world. So I was really proud of everything they were able to accomplish under a challenging and weird environment. So I wanted to thank the postdocs in the group, student and research assistants, and our collaborators at the Metabolomics Core and informationists at the library. You'll be seeing some of their pictures again as I talk about individual projects. So our project was focused on addressing sparsity in metabolomics data analysis. And just the textbook definition of sparse is thinly scattered or distributed. And I've shown something like this in the past in previous update meetings, but I wanted to just define what we mean by sparsity here. You could think about sparsity in individual metabolites due to missing or NA values in the data, either for biological or technical reasons. We can also think of sparsity when you look beyond just a single metabolite, but across metabolites, and thinking about connections between metabolites, whether they're connected in sparse ways in metabolic pathways, or also due to collinearity of highly correlated metabolites in the data. So our work has tried to address sparsity in these different ways. And we had a motivating data and project. We work in large cohort studies. And in particular, a lot of the motivating data and collaboration was through a project on chronic obstructive pulmonary disease, COPD, through a large genetic epidemiology study called COPD Gene, which is also part of TopMed. Just a few words about COPD. It's got a large impact here in the US. It's the number 4 cause of death and affects more than 20 million patients. It is a disease of chronic smoking and aging, but not all smokers develop COPD. So it's very sort of complex and heterogeneous disease. On the right, I have examples of types of phenotypes where you can look at airflow obstruction through spirometry, or can look at percent of emphysema through CT scans. And working within the COPD gene cohort, it's a large genome-wide association study at GWAS, over 10,000 subjects with a lot of data, including genotyping, clinical and imaging phenotyping, multiple time points. They're now in their 3rd year of recruitment, or 3rd visits of recruitment every 5 years. So a collaborator, Russell Bowler, one of the clinical investigators for COPD gene, was very interested in metabolomics through various funding in the past. He generated various profiles in plasma and bronchial alveolar lavage fluid, in human and in mouse, multiple platforms, technologies, replication, and of course, matching omics data and many different kinds of genetic, transcriptomic, and proteomic profiles. And here I have an example from a review, and sort of an image showing different types of pathways that are affected by the chronic smoking, and it affects the development and progression of COPD. So this was a motivating context to develop a lot of our methods, but of course the methods are general for other kinds of data as well. So here's a pathway chart of an overview of we worked on in the last 4 years. It's a simple flow chart of some of the most common steps in a metabolomics data analysis, from data acquisition to acquiring the spectral data, to performing the spectral processing to get a feature matrix, to then doing some additional processing to prepare data for downstream statistical and machine learning analyses that include normalization and imputation, batch correct, and filtering. After that, one may take many different strategies. A univariate analysis that's testing single metabolite at a time. For example, this could identify candidate biomarkers, or performing multivariate analyses, multiple metabolites at a time, and thinking about pathways to aid in interpretation. And finally, of course, identification and any database curation and meta-analyses here. So in black, I've highlighted the steps that we've worked on. The first aim was to look at normalization and other pre-processing methods that can handle sparse data. So that was our first aim. Our second aim was improving the methods for metabolite biomarker discovery that account for sparsity. And the next aim was more of a multivariate approach using a framework called kernel machines that can integrate pathway information to perform analyses at the pathway level or multiple metabolites at a time. And the goal was to develop the methods, software, and use simulations and the test data sets, in particular COPD gene, to create user-friendly software, including manuals and case studies. So those were the overall goals. And here's a summary of what we were able to accomplish. I have sort of in steps in this different flow, from imputation to processing pipeline to looking at reproducibility, to thinking about multiple testing at the univariate step to pathway-based analyses. And this work also culminated in a software database that was developed as part of a supplement. So fortunately, we were able to work with Shankar's group in Metabolomics Workbench. And here's this, it was of interest to summarize, what the different tools and what were their languages, what was the input and output, and what primarily we developed our packages. And in some cases, a GUI interface was relevant for that particular tool. So you don't have to look through all of this, but it kind of gives you a snapshot of the input output and how can this connect with other tools as well. So here is, I'll talk about now individual methods. I first wanted to showcase, it turns out one of the students working on the project had a lot of creative talent and was able to create these fun stickers for our software packages. So I wanted to showcase them. These are R stickers that you can get and stick them on your laptop. So I'm really proud of the work you did. So sometimes you find people have hidden talents beyond just this computation and the science. So I'll walk through each of these relevant to the flow chart that I mentioned before. So thinking about the earlier steps after spectral processing, we have a sort of a matrix now, but often it needs to be additional data processing. This method was called MS Prep. It's sort of a pipeline. It was worked on by Max McGrath. He's also the one who did the stickers, and looks at different pre-analytical processing. And what I mean pre-analytic is to prepare the data for the statistical or machine learning. Often you need additional steps, whether it's summarizing any replicates if they're available, but most commonly filtering out metabolites, imputing missing data if that's a need, and then other methods to transform, normalize, and batch correct data. So this was put into a pipeline as an R package and also available on Metabolomics Workbench. It was based on work earlier in the group, but Max was able to now make it more functional, flexible, and modularized. So you can see that here, sort of a flow chart of the different steps of MS Prep. Each of the steps has its own function, but and then it's modularized in that you can add or remove options. So for example, imputation, there's several ways to impute out there. It has several of the most common packages. You can add more or remove any, and different normalization and transformation steps. So this provided a pipeline that we could then include other sort of other work that we had developed into this pipeline and make that available. So that was MS Prep. So in that pipeline, I mentioned imputation. So this was, as I talked about before, one of the types of sparsity is missing values. So this next tool called May was a way to address sparsity in terms of imputation. So this was a master's thesis project from Jonathan Decker-Mangian, and Ellen Shattuck's a postdoc in the group also helped. And the motivation was to perform a mechanism-aware imputation that missing data may be missing for different reasons, whether it's in the statistical terms, missing not at random, that, for example, a signal may be smaller than the instrument level of detection. It could be missing at random. There could be conditions of the data collection or the processing that induces missingness, and also missing completely at random, just randomly anywhere. It doesn't depend on any other factors. And finally, it could be missing, of course, due to the biological reasons, is that maybe compound is just not there. So as many of you know, that often people sometimes omit missing data, or depending on downstream steps, a lot of machine learning steps may require complete data. So you may need to impute, but that can also introduce bias either way, either omitting or imputing. And a lot of the imputation methods often ignore mechanisms that cause the missingness. So Jonathan's work was a two-step procedure, was to think about maybe we can try to first predict the type of missingness mechanism for a particular value that's not there, and then apply a different imputation algorithm that may be better suited for one or the other. Here we combined MAR and MNAR because those are usually more difficult to separate compared to missing completely at random. So the first step is predict the missingness type with a machine learning approach, and then apply an existing imputation algorithm. And again, it's modularized that different types of algorithms can be included, and we've added some of our own as well. So in his work, the two-step procedure was able to reduce bias for then downstream analyses. The first step, based on simulations and imposing missingness through some existing simulation algorithms, we were able to get high accuracy, and then show also reduction in bias if you had a more specialized technique rather than just a single step approach. We also found certain combinations of existing imputation algorithms and some variations that we developed as well for MCAR versus MNAR. So this is all available as an R package and a REST API. Just came out this year, and it's also available in Metabolomics Workbench. So now suppose we've processed the data, imputed it if that was needed. The next step we were looking into is thinking about reproducibility. And that's what the method MAR examines. So MAR stands for maximum rank reproducibility. This was developed by a postdoc Tushar Ghosh, along with the software development helped by Max McGrath. And the idea is if suppose you have replicate experiments, but it doesn't have to be replicates, it can be any two samples. This was developed in a different omics context, but then now adapted from metabolomics. And the idea is if you take the ranks of different metabolites in the data and examine the rank, it could be ranked based on abundance or any other statistic, fold change, t-statistic, so on. And if you rank them, you can see that maybe here in the beginning, certain at the highest ranks, maybe most abundant, or for other factors, their ranks are similar, so we would consider reproducible. And at some point, the data become noisy, and then they are irreproducible. So that's what the red part is here, that the ranks don't match between the two samples. So this is an extreme example. It's not this clear division, but the idea is, where is this breaking point? And if the further is, then it kind of gives an indication of the reproducibility. So you can then think about reproducibility in different ways. So here's just a flow chart that after processing the data, as I mentioned, then we can look at looking at these maximum ranks, examining this transition between the blue and the red that I showed before. And then you can estimate for each metabolite, all pairs in the study, how many pairs is this considered reproducible, or kind of flipping the problem for each sample pair, how many percent metabolites are reproducible. And this is metric can be used for different reasons. Could identify maybe outlier or unusual metabolites or unusual samples, just to flag them further, maybe QC. It could also be used to compare different processing methods. I've already mentioned before, different normalization or transformation, imputation methods, and maybe based on ones that maybe give higher metrics for this reproducibility. Maybe that's an advantage of a method over another one. So it's just one way to explore the data, again, before moving on to downstream analyses. So MAR, there's an R package, and in this case, it lended itself very well to an R Shiny app. This was published recently, and it's on Metabolomics Workbench, both the package and the Shiny app in Bioconductor. So moving now to, we've processed the data, we've done imputation, we've already looked at some of these kind of quality and reproducibility metrics, and we're ready to move forward to perform a statistical analysis. So a first step may be to do more of a univariate analysis, looking at each metabolite at a time, to looking at associations with an outcome or differences between conditions. So the next method explores that, and it's called DiscoPad. So DiscoPad, actually, we had a lightning talk the other day. So Devala Nandi is a postdoc who worked on this, and DiscoPad stands for Distance Correlation-Based Adjusted P-Value. So as you know, in this high dimensional data setting, it's important to do some kind of adjustment for multiple comparisons. And very commonly used methods are Bonferroni or the false discovery rate. And they have their pros and cons in terms of conservativeness or leniency. But drawing from some of from the genetics world, but it's recently been adapted to metabolomics, is this concept of effective number of tests. And the genetics world, you have SNPs, and they may be in liquid disequilibrium, so very highly correlated. So you don't necessarily are not testing independent SNPs. So some of those concepts also we can be translated here, and there's been actually work by other groups in this area. And the idea is that even though we have P metabolites, there's a smaller number of effective number of tests. And it uses an eigenvalue-based analysis based on a Pearson's correlation between metabolites to try to identify what is this smaller number of a more considered independent tests. What Damalo has worked on is instead of a linear association like Pearson's, a more generalized one based on a distance correlation. And this is work in progress. He'll be wrapping up soon, but so far his simulations on some of the COPD gene data shows that it can mitigate false positives and false negatives in this kind of multiple testing framework. So it improves that balance. And can be used with different kinds of correction methods. So I don't have, so he presented some results the other day, and this is work in progress. Now, so I mentioned univariate analysis, which was this multiple testing procedure that was trying to adjust for that. But we may also want to think in a multivariate setting and not think about each metabolite one at a time, but think about metabolites in groups. Okay, so and that's what this Pearcat approach examines. So Pearcat stands for Pathway Integrated Regression-Based Kernel Association Test, and this was work by student Charlie Comperter and another research assistant, Conrad Severin, who worked on the software. And the idea is to now test an association between a pathway or group metabolites and a phenotype or outcome of interest. So similar to before, we're trying to find biological associations, but now we want to treat the pathway as a unit. But there's often information about connections between the metabolites in a pathway. So that's the pathway connectivity. And to do the multivariate analysis, we use a kernel machine regression framework. But these pathways can often be sparse, not necessarily the pathway itself, but based on what's data collected. Once we map it onto the pathway, we may not have all the nodes. So it could introduce some sparsity. And that could even have problems in terms of power, or even so sparse you can't even test it. So what Charlie worked on is a way to regularize regularization technique over the graph in the pathway to smooth over this sparse or possibly disconnected pathway while still preserving key features of the pathway's topography. So I have a picture of that in the next slide. Here's examples from KEGG where you have to make some more dense graphs to more sparse graphs. And in simulations, we showed that you could also just do this test ignoring the pathway information, but simulations, regardless of the sparsity in the network, including it showed improved power. Even if there was some incomplete or incorrect information, it was still useful. robust, and it could be applied to any networks of any density, even more sparse graphs like this. So showed several advantages. So this is both an R package and also a Shiny app. I think this method lends itself nicely because we can create pretty network graphs. It's hosted also on Metabolomics Workbench. And currently we have a CAG, but we're working with the RAMP group to include RAMP as well. So we have other options for what the databases are included. Okay, finally. So wrapping things up is the last major resource that we worked on through a couple of supplements on our U01. And this method, this database is called MSCat. And we also had a lightning talk the other day from Vlad, who presented that. So this was a team effort that involved very different kinds of expertise from machine learning, from Jonathan, from the information science, from Vlad Bakevsky in the library, and then some of the meta-analysis, Kaiser, also from Manana, but Jerry and Eric Serrano, a rotation student who worked on the GitHub metadata analyses. And finally, a lot of support from the Metabolomics Workbench team. And this was a catalog that it was a curated tracking of metabolomic software in the community. Right now, there's over 400 curated tools. And there have been efforts in the past, but they they weren't a way to automate the curation, or they were only based on, for example, R packages. So we tried to be more comprehensive and tried to design it in a way that was at least semi-automated. It still takes some curation because you still need some of that expert knowledge, but it does have a lot of automated aspects. So here's just a summary, some screenshots from the database. It's a table, with different tool names, information on last updates, operating systems, and so on, and functionality, some database metrics, summarizing programming languages and the functionality and sort of a year. Finally, there were efforts, some preliminary efforts to create a workflow generator. This is actually very challenging once we got into it and realized we tried to create the workflow generator based on functionality. You would do statistical analysis after processing of data, for example. So just looking at that ordering and maybe doing some limits, like if you only wanted to look at command line tools. So then you could create, or you had a particular tool in mind and wanted to see which maybe software could in theory be interoperable with it. So again, it was a first pass, but we realized that this needed more work. So we've been working in the last year on a MSCat version 2.0 to, in addition to include new fields, to do some more automated way of adding some of the field information, because more than half the tools have GitHub repos. Interestingly, in that process, we actually noticed a lot of both good and bad practices that people do in GitHub. So that was good to learn from. And then the new feature to look at the interoperability was more of an empirical approach, is to, instead of looking at theoretical what would be possible, we looked at what was available, what people did in the literature. Which look at every time we find that tool mentioned in a method section of a paper and see what co-occurrence of other tools. So here's an example. You could take one tool, and then we had thousands of papers where maybe we had taken off from PubMed and all the other tools that were mentioned in the methods together, and you could create a network graph. And the size of the node may be how frequently that tool is cited, and the edge of weight is how frequently that pair of tools are mentioned in method sections together. So we figure this complements some of the previous type of workflow generator with some empirical evidence. And in addition, this new MSCat2, we also did some metadata analysis of, based on citations, which tools are popular, and maybe are there any factors that contributed to that popularity based on citations and mentions. And finally, we're trying to work on this handoff for Metabolomics Workbench and how to continue for this tool, this resource to still be available and curated in the future. So just to wrap things up, we have this DiscoPad method that we finished in the summer, extensions to Pearcat. We're thinking about not looking at just one outcome. For example, COPD, there's various COPD severity phenotypes, but there's a lot of covariates, for example, sex and age, that subtypes, how do we extend that pathway-based approach to look at subtypes for outcomes, and also including the RAMP database. I think I mentioned also handing off MSCAT to the Metabolomics Workbench folks. And then just in general, how do we continue the maintenance of the software that we've developed, and how do we continue interactions with the consortium members moving forward? So I was going to advertise the lightning talks, but they actually occurred before the last 2 days. So hopefully you were able to hear those. And then finally, I just want to thank the whole consortium, thanking everybody at NIH and 3C, the DTC group. It's been such a wonderful experience to be part of this group and consortium. So thank you.
Great, thank you. Any questions? We have time for a question or two. Art, I think you.